Assalamu alaikum warahmatullahi wabarakatuh. Welcome everybody. In this video, we are going to talk about modeling of electrical systems as a part of chapter 2, which focuses on mathematical modeling of electrical and mechanical system, in addition to some concept which is related to the mathematical modeling, such as Laplace transform, inverse Laplace transform, differential equation, and transfer function. We have studied how to represent a control system by using transfer function and also by using differential equation, and we said in our course we are focusing more on the transfer function, and we see how the transfer function is important to study the performance of a control system. So in this section we are going to learn how to represent an electrical system by using transfer function. So we are focused on two type of electrical system. One is the passive network or passive circuits, and the other one is the operational amplifier circuit. So in the passive network here, our focus will be on the electric circuit that you already know before during your course of circuit analysis 1, circuit analysis 2, which consists of the passive element like resistor, capacitor, inductor. And in the second part here, we focus more on the operation transfer function of operational amplifier circuit as an electronic element, which is not passive, but it is active here. So actually, there are two methods to find the transfer function of electrical network, one using differential equation and the other using the transform method. So we are going to go through the two methods here, but our focus will be more on the transform method. Since we are in our course, we focus on the classic control system, which is more in S domain. So for the representation of electrical network by using differential equation, or actually here when we say differential equation, we are talking on time domain. So the value of elements here, or the value of the voltage, the current will be V of t, I of t. It's not V of s, I of s. So we are talking, when we talk about the differential equation, we are in the time domain, and the value here of the voltage and the current are represented by in the time domain. So there are several steps we need to follow in order to find the transfer function or to represent this electric circuit by using differential equation. The first one is we need to construct the electric circuit. So we need to draw the electric circuit and highlight the value of the passive element, like the value of resistor, the value of inductor, the value of capacitor, and also the direction of the current in the circuit and the voltage, the input voltage source here. Second, after we represent this or construct this circuit, we need to apply either KVL or KCL, Kirchhoff current law or Kirchhoff voltage law. So after we apply this KVL or KCL, we can write the differential equation for this loop, for example, if we have a single loop. If we have two loops, also we can write two differential equations. If we have three loops, we need to write three differential equations. After we write the differential equation for the circuit, we need to convert this differential equation using the Laplace transform as we learned before. So the differential equation will be converted into Laplace transform. So we will get some equations, and we are going to solve this equation in the S domain. And from this equation, we can find the value of the, or we can find the equation of the transfer function of our system. So here, this table actually shows the relations between the component or the passive component with the voltage and current, and how we can define the value of voltage and current for each element. So as you can see here, this is the resistor here, and this is the Ohm's law. Voltage equal to R, V of t equal to R times IT. This one is Ohm's law, and also the value of the current is equal to VT over R. So nothing changed here. But in the case of the capacitor or in the case of inductor, we have the value of the voltage here is equal to 1 over C integrator from 0 to 1 I of tau d tau. And the value of the voltage here, I of t equal to C dVt over dt. Actually, these relations you already learned during your course of circuit analysis 2. When you talk about the AC circuit, we talk about the voltage and current relation of the capacitor, voltage and current relation of the inductor also. So actually this if we can see through from this table here, we can find some differential equation or differential parameter or part of differential equation. So in the first element here, which is the capacitor, we can see I of t equal to c dv of t over dt. So this represents differential equation here, differential equation. And this will be also a part of differential equation, like vt equal to l di over dt. So we are going to see how we can use these equations of voltage and current to write the equation of the loop or the differential equation of the loop. Then from this differential equation, we can find the transfer function. We have this example, which is a simple example, consists of three passive elements connected in series with a voltage source. So we have inductor, resistor, and capacitor with a value L, R, and C. And we have one voltage source here. And he said he need to define the transfer function that relate between the capacitor voltage VC to the input voltage VS using differential equation method. Here, already mentioned that we need to use differential equation method. So in order to find the transfer function using differential equation method, we need to follow the step that we mentioned earlier, the four steps that we have. So we need to construct the electric circuit here. So the electric circuit already there, the voltage source, the direction of the current, the value of the element already there. But also the most important, we need to identify what is the input to our system and what is the output. So the transfer function is a function that relates between the output and input. Here, in this example, he said the output is across the capacitor voltage. So this is VCT represent the output of our network and VT represent the input of our network. But it's not always like that. So in any similar example, you need to focus which is the output. So usually the output is given here. He said the output is the capacitor voltage. So since the output is the capacitor voltage, so this is the capacitor and this is the output here, and here is the input. So we need to find a relation between the output and input, and this will be the transfer function. So after we construct the circuit here, we are going to write the equation, which is the relate between the input and the output of our system. So if we can see here in this circuit, we have these three elements which consume the these three elements, which is the passive elements, and we have here is the source or the voltage source. If we want to write the the equation of this loop using KVL, so we have actually four voltage. When we talk about KVL, that means Kirchhoff voltage law. So we need to write the equation using KVL. So we have the voltage of the source, we have the voltage of the inductor, which is VL, the voltage of the resistor, which is VR, the voltage of the capacitor, which is VCT. So we have here VL, and we have here VR, and we have here VCT. So in order to write the equation will be here. The voltage source or the summation of all voltage equal to 0, or the input voltage is equal to the output voltage. Okay, so here we have the input voltage is VT, and the output voltage or the voltage or the voltage drop will be summing of the voltage drop across the inductor, resistor, and capacitor. So VT will equal to VLT, VRT, and VCT. Okay, now we need to, in order to find the differential equation, we need to represent this voltage by their value in terms of the impedance and the current. So for VLT here, as we see in the previous table here, we said VLT is equal to L di over dt. So we go there. So this is VL will be represented by L di over dt, and this one is equal to the voltage of the inductor. Then how about VR? Actually, the voltage of resistor is the same, is equal to I times or R times IT. So this is R times IT as it is here. VT is equal to R times IT. Nothing changed. Okay. Then the third part will be the VCT. We will keep it VCT same. Why we will keep it here? Because we need the VCS and we need the VS. So here we need to keep VCT and Vt in our equation in order to find the transfer function. So these two elements, we are not going to substitute them in terms of the current. Okay, so by considering the, as we can see here, we have only one current in our circuit because this is a series circuit. So we only have a current which goes through the inductor, the resistor, and the capacitor. So IT here will equal to ICT. That means the current of the loop is the same as the current of the capacitor. But actually the current of the capacitor is equal to CdVCT over dt. From where we got this one? Actually this is how we can represent the capacitor current from this table. So ICT here is equal to CdVt over dt. Same as we got it here. ICT is equal to CdVCT over dt. Okay, so now the value of IT here in our equation will be replaced by this value. Why? Because we want to keep only the variables which is related to the transfer function. So we need to keep VC or and VT. We don't want to see IT. We don't want to see any other variable which is like VL or VR and so on. Okay, so we are going to substitute this value into our main equation here. So we will keep Vt will equal to L d over dt, but we have it here. This it will be replaced by C dvct over dt. And here in the second one, we have Vc, it will keep Vc. We have here Rit, this It also will be replaced by this one. So as we can see here, we are substituting equation 2 in equation 1. So this is the equation become Vt also still the same because we need to see Vt here, and Vct also still there. We only replace the value of I of t. So I of t here is replaced by C dvct over dt, and I of t here is replaced by dvct over dt. The same. This is the value of I. This represents the value of it, and this represents the value of it or I of t. Okay. Now we can simplify this differential equation because we have here C is constant. C will go here outside, LC, D multiplied by D, so we have D square, then VCT, still VCT, DT will go down with DT here, so we have to the numerator here, the denominator, I mean, it's go from the to the denominator here, so we have DT square plus RC, this is RC, then dVCT over DT. So the same here, dVCT over dt there and plus VCT. Now this our differential equation. This the what we can call it the differential equation of this circuit of this electrical circuit. Now the next step after we got the differential equation, the next step here he said after we got the differential equation, we need to use convert the differential equation using Laplace transform. So we are going to convert the differential equation from time domain into S domain. So this equation here, in order to find the Laplace transform for this equation, each t here will become S, each v small become v capital here. So vt here become vs. So when we apply Laplace, as we learned before, vt become vs. Then LC d square over dt square, this d square over dt square, actually when we convert it by using Laplace transform, it will give you s square, and d over dt will give you s, because each d over dt give you one s. If you have d square over dt square, you have s square. If you have d cubic over dt cubic, you have s cubic. Okay, since when we find the transfer function, our initial condition assumed to be 0, so we are not considering any initial condition here, only any differential value here will be converted into 1s or s to the power of 1. Then if you have square, it's become s square. If you have cubic, so it's become s cubic. So these are the components here. We have LC S square, and we have VC here, VC here, VC here, or the VCT convert into VCS, okay, and it taken outside the bracket here, so it's become a common. So and at the last one VC is give you 1 here. So we have LCS square plus RCS plus 1 VCS equal to VS. So this is how we convert this differential equation using Laplace transform. Using Laplace transform, we got this equation now. Okay, so now from this equation we can solve it for transfer function. What is the transfer function? Our transfer function is equal to VCS over VS. It is the output over the input. So this is the part or the left side of our equation transfer function, which is VCS over VS will equal to what? VCS over VS here. That means all these parameter will go to the other side and it's become 1 over LCS square plus RCS plus 1. So then we are going to divide over LC for the numerator over LC, the denominator over LC to remove the operator or the variables. I mean the coefficient of S square. So to get S square, so we have S square plus R over LS plus 1 over LC. So this will be our transfer function. If we have, if we assume that all the value here R equal to L equal to C, I mean the value of resistance equal to 1 ohm, the value of inductor is equal to 1 Henry, the value of capacitor equal to 1 farad, for example. So this transfer function can be simplified to become VC over VS equal to 1 over S square plus S plus 1. So this will be the transfer function if we substitute for the value of L, C, and R. But actually the system transfer function or the transfer function of that electrical system that we have, or the series electric circuit that we have, is equal to 1 over LC over S square plus R over LS plus 1 over CS. So this is the transfer function actually that we have. This is the transfer function that we have for the electric circuit using the differential equation method. Okay, later on we will see how to find this transfer function by using the transform method. Okay, so by using the transform method, here, we need to convert all elements of our electric circuit into the S domain. So the first step, we need to replace the passive elements like resistor, capacitor, inductor to their values, to their impedances values. So I mean we are not going to say only L and C for the case of the inductor and capacitor, but we need to represent its impedance. So what is the impedance of L? It will be XL as we learn in the circuit analysis, or it will be XC for the capacitor. So we need to represent the value of XL and XC. And in the control circuit here, the value of XL and XC here will be in the S domain in terms of the value of S operator. Okay, after we represent these elements in the S domain, we are going to replace also all sources and time variables with their Laplace transform. So instead of saying Vt, we are going to say V of S. Instead of saying I of t, we are going to say I of s. So all the voltage and current variables here will, which is in the time domain, will be converted into the S domain. Then we are going to assume the direction for the current in our mesh, or at the voltage at our nodes. So if we are going to use the mesh analysis, so we need to assume the direction of the current like I1, I2, I3 in each mesh. What is the value, what's the direction of the current? If we are going to use the nodal analysis, we need to assume the polarity of the voltage, V1, V2, V3. Okay, then we are going to use either Kirchhoff voltage or Kirchhoff current laws to write the equations, either the mesh equation or the node equation as we learn in circuit analysis. Okay, After we write the equation, we are going to solve the equations by using any method for solving equation, either substitution, addition, subtraction, using matrix, using determinant. But I recommend you to use the Kramer's rule, because Kramer's rule actually is more uh, easier to solve the equation, especially if you have more than two equations. I mean, if you have three equations, four equations, so in this case you are going to use Kramer's rule. So you are going to solve only for the variable that you want to know. I mean, you are not going to solve for all variables. So if I want the value of I2, so I am going to solve only the value of I2 only, or the equation which is related to I2 only. Okay. After that, after we solve the equation, we can find the relation between the input and output of our electric circuit. So from this relation, we can find the transfer function of our circuit. So we are going to also to compare or to show the relation between the passive elements here, which is capacitor, resistor, and inductor in the S domain. Previously, we saw this, we see these values or this component with the voltage current relation in the time domain, and we said the voltage of capacitor, the current of capacitor, voltage of resistor, and current of resistor, same voltage of inductor, current of inductor, all in the time domain. In this table, we will see it in the frequency on the in the S domain. So we can see here, the first is the value of impedance. As we learned before, the value of impedance, I mean the reactance of the capacitor is equal, which is XC, is equal to J 1 over J omega C, or equal to negative J over omega C. And but here in the control system, we are going to use in S this impedance value in S domain. So the value of XC here is equal to 1 over CS without J. Okay, 1 over CS, because S here is the frequency operator, which may include either real value and or complex number. The second one is here the admittance, which is also the equal to Is over Vs. For this capacitor, the admittance will be the value is equal to Cs. The value of the voltage for the capacitor here, which is based on Ohm's law, Vcs equal to S over Cs. It is the same like the value of the current times the value of the impedance. So it's equal to Is times 1 over Cs. So it's give you Is over Cs. Same for the resistor here, but in the case of the resistor, actually, we do not have the S operator here because the resistance is not affected by the frequency. So R is equal to R either in the time domain or in the S domain. So the value of R is the same, and the value of admittance is equal to 1 over R is the same. The voltage is equal to RIS based on Ohm's. In the case of the inductor here, the value of inductor or the reactance of inductor or XL here is equal to LS. Instead of J omega L that we have in the circuit analysis 2, it was J omega L. Now it is equal to LS. So the J omega replaced by the operator S. Okay, and the admittance YS is equal to 1 over LS. The value of the voltage is the same. Here become VLS is equal to XLS XLFS times IS, or LS times IS. So if we want to use this transform method to solve our transfer function, we need to replace any capacitor by using 1 over CS, any resistor by R, any inductor by LS. Based on the value of L and the value of C here, this value will be changed. So if you have capacitor is equal to 5 farad, so it's become 1 over 5s. If the capacitor is equal to 2 farad, so it's equal to 1 over 2s. Same for the inductor here. If the inductor is 2 Henry, so the value of impedance here become 2s. If the inductor is 10 Henry, so the value of the impedance become 10s, and so on. So we are going to repeat the example one here, but to solve or to find the transfer function which relate between the VCS, same VCS, which is the voltage of the capacitor, and the input voltage. So the transfer function is equal to VCS over VS. Okay, but we are going to use the transform method instead of using the differential equation method. So the transform method, we said in the beginning, we are going to focus more during mathematical modeling on the transform method, because actually it's a little bit easier than the differential equation method. And also our course here, which is more on classical control system, which focus on the using transfer function instead of using differential equation. So how we can, what are the steps we need to follow in order to drive, or in order to find the transfer function for this electric circuit? The first step was to transfer these elements into the S domain. So instead of L, I should have SL. Instead of R, I should have R. Instead of C, I should have 1 over CS. Okay, so these all elements, and instead of VT, I should have VS. Instead of IT, I should have IS. So all this circuit is transformed to this circuit. So this one in the time domain, and this one in the S domain now. So you can see here VT is VS, IT is IS, and L become LS, R stay R, no change, C become 1 over CS, and the VCT here become VCS. Okay, after you redraw the circuit and you represent this element in the S domain, so it's easy for you to write the equation of your loop in the S domain now. So if we want to write the equation for one loop here, actually a number of equation depends on number of loops. So if you have one loop, so you are going to write only one equation. If you have two loops, you are going to write two equations. If you have three loops, you are going to write three equations, and so on. Okay, this if you are going to use the mesh analysis. If you prefer to use nodal analysis, also you need to find how many nodes do we have, and based on the number of nodes, you will have number of equation. If you have one node, one equation, two nodes, two equation, three nodes, three equation, and so on. Okay, so here we have one loop or one mesh here. If we want to write the equation by using KVL, just you need to find the summation of all impedance in this loop. How many impedance do we have? We have three impedance, LS, R, 1 over CS. So you need to just add this impedance times the current IS equal to, on the right side of your equation will be the applied voltage of in your circuit. So how many voltage source do we have? We have only one voltage source. Don't say this is voltage source. This is capacitor. It's not a voltage source. Okay. So the summation of the impedances. So here we have the summation of impedances. LS plus R plus 1 over CS. This is the summation of all impedance in your loop times the current value. So this is the current value, which is IS, the current of the loop, which is IS. This is on the left side. On the right side, you have the applied voltage source. So how many voltage source? We have one voltage source, which is VS. You just put it VS. Now, from this equation, you can find the relation between the input voltage, which is VS, and the output voltage, which is VCS. But we cannot see the VCS here in this side. Only we have VS. So how we can find VCS? Actually, the current, as we mentioned before in the previous example, we said the current here is only one current. So the current which go through the inductor, same as resistor, same as capacitor. So if I can replace the current here by using the voltage of the capacitor. So the value here, you can see, the first we need to simplify this one. Is over Vs equal to 1 over Ls plus R plus 1 over Cs. But here the value of Is is equal, which is the current here. Is is equal to Ics, or the current which go through the capacitor, is the same. What is the value of Ics? As we can see here from this example, as we can see here from the formula, the voltage of capacitor is equal to current over Cs. So the current here is equal to Cs times Vcs. Ics is equal to Vcs times Cs. So you can see here, we just substitute for the value here. Is equal to Cs Vcs. We are going to replace this value of the current by this value of the capacitor voltage times C times S. So now we have Cs Vcs over Vs. So the current here, the value of is replaced by the value of cs vcs. Okay, so we have cs vcs over vs will equal to the same value on the right side here, and this value actually is constant. L is constant, r is constant, c is constant. Only the variable here is the s operator, or the frequency operator, which is s here. Okay, then we are going to simplify because our transfer function is vcs over vs. So this cs will be transferred to the other side. So the formula become VCS over VS is equal to 1 over LC S square plus RCS plus 1. Now we are going to divide the numerator and denominator over LC here. Both we will divide it over LC, so become 1 over LC. This become L square R over LS plus 1 over LC. And this transfer function here, this value of transfer function, it is the same as the transfer function that we got from the previous example in example 1. Okay, so the transfer function can be found by two methods, one using differential equation and one using transform method directly. Actually, the different in number of steps that we will use to solve the transfer function in both methods will be clear when you have multiple loops or multiple nodes. For this single loop, maybe the number of steps is close to each other or maybe the same. But if you have more loops, so it will be difficult to use the differential equation, and it's easy to write the equation using the transform method. When, for example, in this exercise here, we have electric circuit consists of three loops. So we have one loop here, another loop, and third loop. So we have three loops, and we need to find the transfer function, which is relate between VLS, which is the voltage across the inductor here, and the VS, which is the input voltage. So we need to find the transfer function, which is VLS over VS, by using the transform method. Okay, so actually the step to find this one is the same like in the previous example. The first, we need to redraw the circuit in the S domain. So each element here will be replaced by its impedance value, and each time variable will be replaced by its Laplace transform. So Vt become Vs, Vlt become Vls. Also, we need to define the direction of the current in each loop. So we have here I1, I2, I3. With the direction, we should assume the direction either clockwise or counterclockwise, depends on your assumption. After you redraw the circuit with this, with indicating this value, you are going to write the equation. So you can see here, this is the circuit after we draw it in the S domain. So the value of 1 Henry become Ls, which is 1 times S equal to S. The value of resistor still 1. The value of resistor still 1, no change. The value of impedance here, Ls, also, it's equal to 1 times S, so it's S, because we have the impedance value, we have the impedance value here is equal to 1 Henry, 1 Henry. So it's become Ls, which is 1 times S, so it's equal to S. Okay. Then the variable, the Vt here become Vs, Vlt become Vls, and we assume the current with their direction, which is I1s, I2s, and I3s. So after we finish this step, we can easily write three equations in the S domain. So the three equation here, each equation actually represent the summation, I mean, for the node that we are going to consider. So for example, if I want to write the equation for the loop number 1 or the mesh number 1 here, the coefficient of I1 will be the summation of all impedance in this loop. So in loop 1, we have how many impedance? We have two impedance. We have this resistor and this inductor. So we have two impedance, so the coefficient of I1 will be 1 plus S. So we have 1 plus S I1. Okay. Now, in this equation, the other loops become, there is some elements with other loops. So we have S is in common with the I2, and we have 1 is in common with I3. I mean, this S is common between loop 1, loop 2, this resistor is common between loop 1 and loop 3. So the sign of these common elements will be negative. So because we are focusing on loop 1 now, the other will be negative. So we have negative Si2, I mean minus Si2 minus I3, and on the right side we said we need to write the applied voltage on this loop. So how many applied voltage source? We have only one, so we just write Vs. Okay, so this is how to write the equation for or the mesh equation in order to solve them to find the transfer function. The second equation will be written from loop number 2. So in the loop number 2 or mesh number 2 here, the summation of impedances of this loop will be multiplied by I2 and it become positive. So here we have how many elements? We have 3, 1 plus S plus S. So 1 plus S plus S, that means 1 plus 2S. So this 1 plus 2S here is the coefficient of I2 and it is positive. Why? Because in equation 2 our focus on loop number 2. So loop number 2 will become positive, while the other loop which has common element with this loop will be negative impedance value. So here, if I am in loop 2, I have this S in common with loop 1, so it's become negative SI1. Negative, as we can see here, negative SI1. Okay. So here we have negative SI1, and this loop I2 has common element with loop 3, which is the value of resistance 1, so it's become negative 1. Here we have negative 1 I3. This is how to write the equation number 2. This is the equation number 1, this equation number 2, and here we have the third equation or equation number 3. Okay, now for the loop number 3, the coefficient of I3 will be positive and will be the summation of all impedances. So we have S plus 1 plus 1, so become S plus 2. So this is positive S plus 2 is the coefficient for I3. For I2, there is one element in common which is negative 1. So we have negative 1 here. For I1, we have one element in common which is also negative 1. So we have negative 1 here. You can see here in the equation number 2 and equation 3, on the right side of equation we put 0, 0 because we do not have any voltage source. So there is no voltage source only in loop number 1. So in loop number 1 we have this value of Vs. But loop number 2, is there any voltage source here? There is no voltage source. Loop number 3, is there any voltage source applied to this loop? No. So we put it 0. So these are the three equations that we need to write for this loop, for this electric circuit. After we write these equations, we need to solve these three equations. But when we solve this equation, we need to consider what are the variables that we need to keep in our equation to find the direct relation for our transfer function. So in the question here, he said the transfer function is relate between VLS and Vs. So is equal to VLS over Vs. So I need to solve the equation which gives me a relation between Vs and VLS. So here the solving the mesh equation by using Cramer's rule. So actually when we use Cramer's rule, we need to find the common determinant, which is delta, and the common determinant is delta is here in the denominator, which is the coefficient of all variables. So s plus 1, negative s, negative 1. Then here we have negative s, 2s plus 1, this is negative s, 2s plus 1, and negative 1 here. Then we have the third one, which is the negative 1. Here is we have negative 1. Then we have also negative 1. This is negative 1. And the third one is s plus 2. So this is the value, we call it delta. So the value of delta here, and we have also the numerator here represent the value of delta I2. From where we got delta I2, we replace the column number 2 in the delta by the coefficient of I2. So these columns here is which is the coefficient of I2 is replaced by the right variables here, or the right side of equation in the three equations. So the right side of this equation is Vs, so we put it here. Then the right side, the second equation is 0, we put it here. Then the third is 0, so we put it here. So now we can, by opening this determinant, by using any method for opening determinant based on your knowledge in the mathematical, so you can use either the any method for opening this determinant to find, you will get this value. Now after you open this determinant and that determinant, you will get this value here, which is s square plus 2s plus 1 vs, because we have here vs, so vs will be stay here. Then s times s square plus 5s plus 2. Okay, now I have a relation between I2 and Vs, but my transfer function need to relate between VL and Vs, not I2. I don't want to see I2. So we are going to replace I2 by its value in term of VL. Since I2 go through this loop which has the VLS, so I can replace I2 by VLS. So I2 go through this inductor or this impedance. So the value of the VLS here is equal to S times I2 of S. Based on this equation using Ohm's law, just the value of current times the value of impedance. Voltage is equal to current times impedance. Okay, so the voltage is VL, the current is I2, the impedance is S. Okay, now VL is equal to S I2 of S. Now this I2 here will be replaced by VLS over S, because I have I2S here. I2S will equal to VLS over S, so I will put here VLS over S. Okay, after we put this VLS over S on this side, S will be, when we make cross multiplication here, in order to find the relation between, not cross multiplication, we are going to take to divide over Vs, and this will be multiplied by S here. So S, this S here will be go with that S. So we still have S square plus 2S plus 1 over S square plus 5S plus 2 times Vs. Now the transfer function is equal to VLS over Vs, and this is the based on the question. He said the transfer function which is related between the output voltage of inductor and the input voltage. So it's become VLS over Vs is equal to S square plus 2S plus 1 over S square plus 5S plus 2, and this will be the transfer function. So we can see here how we solve or how we find the transfer function of electric circuit, which consists of three meshes here, using the transform method. Please go and you have to revise how to solve the equations using Cramer's rule, because this is the simplest way to solve multiple equation. Because you can see here we only solve the value of I2. We don't need to find I1 and I3 here, because we only need I2. Why I2? Because actually I2 has a direct relation with the output voltage here. I2 has a direct relation with VLS. For that, I do not go to solve I1, because I1 is here. So I1 is here is related with VS, but it's not related with VLS. I3, it doesn't have any relation with VLS. For that, we just using Cramer's rule to solve the value for I2 only. So from this value of I2, we have relation between VS, and then we convert this I2 in terms of VLS. Okay. There are several examples, several solved examples actually in the slides. You can refer it to to understand more about how to write or how to find the transfer function of electrical circuits which consist of passive elements. In the second part, we will learn how to find the transfer function for operational amplifier circuits. So when we talk about operational amplifier, actually it's not passive element, it's active element. Why? Because it will has a direct impact on the input voltage or the input of the control system. It will use to amplify the signal here. And actually the operational amplifier, it has some features like a high input impedance, low output impedance, and also high gain. And all these features make it a good candidate to be used in the control system. In terms of the operation amplifier of derivative operation amplifier, actually, which has two inputs, V1 and V2, we have two types actually here. We have the inverting operational amplifier and we have non-inverting operational amplifier. The difference between inverting and non-inverting: in the case of inverting, the positive terminal or V2 here is connected to the ground. For that, the output voltage will has a negative value or a negative value comparing with the input, because the input, one of the input here is connected to the ground. For that, its transfer function will be in the form of V out over V in equal to negative Z2 over Z1, where Z2 is the output impedance, Z1 is the input impedance. You can see here in the figure, for the inverting operation amplifier, this is the V in, this is the V out, this is the input impedance which is Z1, this is the output impedance which is Z. Okay, so if you have or if you are given an inverting operation amplifier, you should use this transfer function for negative Z2 over Z1. So whatever is the value of Z2 or Z1, you will get, or you can derive or calculate the value of transfer function for such operation amplifier circuit. The second type of operational amplifier circuit here is the non-inverting. And non-inverting here, that means the input and output, they are there is or the terminal or the positive terminal of your inverter here is not sorry, your amplifier is not connected to the ground. So we have the input is go through the positive terminal, and the negative terminal, which is V1 here, is connected to the output and also at the same time through the input impedance to the ground. So in this case, this we call it non-inverting. So the transfer function does not have any negative sign here. So V out over V in will equal to Z1 plus Z2 over Z1. So you need to use this formula or that formula to derive the transfer function for operation amplifier circuit, either for inverting or non-inverting. Depends on the time. We have this example here. And this example, he said find the transfer function for the given operation amplifier, and he gave you this operation amplifier. The first thing you need to do when you given such example or such question here, you need to see is it inverting or non-inverting. So you check the V2 or the terminal V2 or the positive terminal of your amplifier. Is it connected to the ground? Yes, it's connected, so it is inverting. Is connected to the ground here, so it is inverting amplifier. Since it is inverting amplifier, you are going to use the formula of the inverting transfer function of amplifier. V out over V in equal to negative Z2 over Z1. This is the first step. After you know which type of your operation amplifier, you are going to substitute for the value of Z2 and Z1. So how to find the value of Z2? Actually, you will see what Z2 is represent the output impedance. So in this case, we have the output impedance consists of resistor connected in series with a capacitor. The input impedance is represent a resistor connected in parallel with the capacitor. So you need to calculate what is the equivalent impedance here for the output, what is the equivalent impedance of the input, by using the method that you learned during circuit analysis, either one or two. So you need to know here what is the value of the impedance for the series and for the parallel. So in the case of the series here, the value will be R2 plus J or R2 plus 1 over C2S. Okay, so actually this value should be in the S domain, not in the value of in the normal value. Okay, and here also the value of S should be in the S domain. The value of R is still the same, either time domain or frequency domain. but the value of C will be changed. Okay, so when we need to calculate Z1 and Z2, so if we start with Z1 here, Z1 is two elements in parallel. So you need to find the impedance 1, which is Z1, for the impedance 1, which is X1, and the impedance for 2, which is R1 here. I mean, this is C1, this is R1. Then you find the relation between them, I mean the equivalent value for this impedance. So Z1 here will be equal to 1 over, since it's in parallel, so it's like the case of the parallel resistor, it's 1 over R1 plus 1 over R2 plus 1 over R3 equal to 1 over R equivalent. So if you want R equivalent, it's become 1 over R1 plus 1 over R2. So here, same. So Z1 become 1 over, the first impedance is C1s. Why C1s? Because we said the representation for the impedance for the capacitor is equal to 1 over Cs. 1 over Cs. So you have here 1 over Cs. So it's become C1s. Then for the resistor here, it's R1, but it's, since it is in parallel, so become 1 over R1. Okay. So you just need to substitute for the value here, for the value of the resistor and the value of the inductor. So the value of R1 here is equal to 360 kilo ohm. So you need to consider the units. Since it is in kilo ohm here, you need to convert it into ohm. So it's become 360 times 10 to the power of 3. So you convert it into ohm. The value of the capacitor is 5.6 microfarad. So you need to convert into farad. So it's become 5.6 times 10 to the power of negative 6 and times S. Okay. So it's become 5.6 here. But you need, don't forget to write the S here, because S here is represent J omega in the that you know previously how we calculate the reactance of a capacitor, which is 1 over J omega C. So here it is 1 over Cs. So you just write the value of C1 times S. Okay. Then you simplify this numbering. You do the calculation for this one to simplify. It's become like 360 times 10 to the power of 3 over 2.016 S plus 1. So this will be the transfer, the value of Z1. Okay. This is Z1. Then this Z1 will be placed here. After that, you calculate the value of Z2, which is R2 plus XC2 or plus 1 over C2S. Okay, 1 over C2S. This is the value of the impedance for the capacitor, and this is the resistor, and both of them are connected in series. So nothing. So you just make plus. So the value of a resistor here is 220 kilo ohm times 10 to the power of 3, because it is kilo ohm here, plus 10 over 7, which is the value here because it's microfarad, 0.1, so it's become 10 to the power of negative 6, 0.1, so it's become 10 to the power of negative 7. It is in the denominator here. You want to take it up to the numerator, so it's become 10 to the power of 7. And the value of S is still in the denominator here, so it's S. Now, this, the value of Z2 will be replace this Z2 here. After you substitute for Z2 by its value, Z1 by its value, you will find the value of transfer function, which is V out over V in negative. Don't forget this negative for the inverting operational amplifier. Okay, so your transfer function become V out over V in equal to this value. Always transfer function is a function of S. So you are going to see S square, S cubic, S to the power of 4, S to the power of 5. So it depends on the highest power of S here. So, but it is a function of S, which is V, relate between V out over V in. Thank you. Also, there are some extra examples and exercise in the slide. You can refer to it for more details.